Robert. It's not the introduction to the facilitation.
Okay, thank you. Um, all right, so yeah, so I guess we can get started. Okay, yeah, so hello everybody. My name is Robert. I'm Lapchi's PhD student, currently 5th year. And today I'll be giving a talk about our recent paper, Derandomizing matrix concentration inequalities from free probability. So this is joint work with my advisor Lapchi and Hongzhou from Fuzhou University. Okay, so yeah, let's just get right into it. So with matrix concentration inequality, we basically want to study the eigenvalue statistics of random matrices. So in particular, consider the following model where we have a matrix X, which is equal to A0 plus X1 plus X2 and so on, where each Xi is a symmetric random matrix, a D by D random matrix with zero mean. So basically a sum of independent random matrices. And we want to study its spectral statistics. For example, we may want to ask about its maximum eigenvalue or operator norm. The expectation, sorry, we might want to look at the expectation of its maximum eigenvalue or operator norm. Or we may want to look at, let's say, the Schatten P norm of the eigenvalues, which, as we all know, can be written as summation I lambda I to the power of P, all to the power of 1 over P. Okay, so actually, let me pause for a second because there's a few people walking.
While you're pausing, can we get rid of the dialogue?
Oh, which one? Oh, the okay here? Oh. Let's see. All right. All right. Okay, yeah. So for those who are just coming in, this is yeah. So the name of the talk. Let me go back to the beginning here. For those coming in, the name of the talk is our recent paper on de-randomizing matrix concentration inequalities from free probability. And okay, so matrix concentration, we want to study the eigenvalue statistics of random matrices. In particular, the model we'll be considering is random matrices that is a sum of independent symmetric random matrices with zero mean. And the kinds of eigenvalue statistics we want to study are things like the expected operator norm or maximum eigenvalue, for example, or the Schatten P norm of the eigenvalues, which we can write as the trace, as the expectation of the normalized trace of x to the p, all raised to the power of 1 over p, right? Because the trace of a matrix is just the sum of the eigenvalues. So yeah, so this p norm is another important spectral statistics. And in particular, if you take p going to infinity, it is exactly equal to the maximum eigenvalue. And moreover, whenever p is on the order of log d, this p norm and the eigenvalue is within a constant factor of each other. And another spectral statistics that we may want to study is the support of the entire spectrum if we're more ambitious. So not only do I want to know where the maximum eigenvalue is, I want to know where all the eigenvalues are. And so these are the kind of spectral statistics that we're interested in. And okay, so let me first give you some classical results. So the non-commutative Khinchin inequality basically says that if your matrix is a Gaussian matrix, meaning that its entries are jointly Gaussian, then essentially we can bound the expected norm by this matrix variance parameter. So what is the matrix variance parameter? Well, basically, if you think about, so basically, you know, the classical variance is the expectation of x minus e of x squared. In this case, the matrix variance is the norm, is the maximum eigenvalue of the matrix x minus e of x squared. And another way to think about this is that whenever I have a Gaussian matrix, I can write it as a linear combination of deterministic matrices where the coefficients are like standard independent Gaussians. And this matrix concentration and this matrix variance is just the norm of the sum of the squared coefficients, of the sum squared matrix coefficients. Right? So this matrix variance parameter is very important. So make sure that you remember this. So this is for Gaussian matrices. And so for Gaussian matrices, we see that the expected norm is upper bounded by sigma x times root log d. And then for non-Gaussian matrices, we have a similar bound where we have an additional error term where if you have x being a sum of independent xi's, and the xi's are independent with norm at most row, as long as this row is small, then we see that you get a sort of a similar bound as in the Gaussian case. Yeah. So that you can think of this as sort of like a matrix analog of like CLT and those kind of things. Yeah. And then in addition to bounding the expected norm, we can also bound the tail. We can also give tail bounds on these random on the norm of the matrices using things like matrix Chernoff, matrix Bernstein, or the Gaussian Lipschitz concentration inequality. All these kind of classical. So all these are classical results. And what you may notice is that in general, your norm bounds are going to lose a factor of root log d, something that's dependent on the dimension. So the natural question is that are these classical matrix bounds actually tight? So let me give you one example where they are tight. Consider when you have a diagonal matrix, a diagonal Gaussian matrix, where the diagonal entries are independent Gaussians. And here we see that the maximum eigenvalue is just the maximum of these Gaussians. And we know that the expectation of this is on the order of root log d. On the other hand, we can verify that sigma x, sorry, I should say sigma d, right? The sigma of this matrix is 1, right? So this is so the classical Khinchin inequality is tight. We cannot avoid losing this log. On the other hand, consider this matrix called the Gaussian orthogonal ensemble, or GOE matrix, which is a random symmetric Gaussian matrix with independent entries. So this matrix also and is normalized so that sigma x is equal to 1. Again, just like the matrix, just like the diagonal matrix. But with this matrix, it turns out that actually the expectation of the norm of this matrix is equal to 2 plus little o of 1. And as dimension d goes to infinity, it basically approaches 2. This tells you that actually in this case, the root log d is not tight. Right? So we don't want to lose this root log d in the second case. And okay, so then when are these tight? Well, in the tight case, we see that you can write the matrix as a linear combination of these chi transpose, where the chi i's are standard basis vectors, and see that these standard basis vectors are commuting with each other. Like the sum of these matrices are all commuting with each other. And whenever you have these commutative behavior, then the classical inequalities are tight. But in the other case, we can write it as summation ij, gij, chi ij plus chi gi. So in this case, these coefficient matrices are not tight. Sorry, are not commutative. And in the non-commutative settings, it seems like you can get much better bounds on the expected norm than in the commutative setting. So the question that was asked by the recent work of Bandera, Bodiharjo, and Van Handel is that can we sort of quantify how non-commutative a matrix is? And using this quantification of non-commutativity, can we get sharper matrix concentration inequalities? Right, so this is sort of like the underlying idea behind their work.
Does anything change? Does everything go through fine if the values of your random matrix are complex? Let's say.
Yeah, it's the same idea. Yeah.
Just want to check.
Right. Yeah. Any other questions?
Is there any intuitive explanation why commutativity should show up in terms of how tight the inequality is?
Yes, but I will not get into that for this talk, but we can discuss the intuitive reasons afterwards. Yeah. It has to do with it has to do with non-crossing combinatorics.
Right.
Yeah. It has to do with there's actually some nice combinatorial reasons for this, but for the purpose of this talk, I don't really have time to get to it, but we can talk afterwards about this. Yeah. Okay. Yeah. So so basically, what they did is that they discovered this idea called intrinsic freeness, which basically measures how non-commutative a matrix is. So given our random matrix X, we define the covariance matrix of this matrix to be the bigger d squared by d squared dimensional matrix, which is just the covariance matrix of X as a d squared dimensional random vector. So forget that it's a matrix for a second and just treat it as a big vector. This is a d squared by d squared matrix that gives you the covariance of this vector, whose entries give you the covariance of this vector. And we're going to define this parameter nu x squared to be so the squared here should not be there. Sorry. This nu x squared is going to be the maximum eigenvalue of this covariance matrix. Okay, so ignore the square on the covariance. That shouldn't be there. The typo, sorry. Okay, so the nu x squared is the maximum eigenvalue of this covariance matrix. And it turns out that as long as nu x is much less than sigma x, the matrix variance, then the matrix is more non-commutative. So to give an intuitive reason why is because if this quantity is small, then you can think of this as saying that the randomness of the matrix is sort of uniformly spread over all of its entries. Right. Okay, so what we show, yeah. Yeah, the next slide will actually explain this a bit more. Yeah. Okay. So what they showed in the BBVH is that when you have the Gaussian model, x equals summation I G I A I, then it turns out that the expectation of x can be bounded, the expectation of the norm can be bounded by 2 sigma x plus this error term that depends on the geometric mean between the sigma and the nu parameters, plus some log factors. So as long as nu is much less than sigma, basically this error is small compared to sigma. And you get a very sharp bound of sigma x without the log factor. Yeah. Any questions? Okay. And
So tied up to the log factor, the log 3/4.
yeah, so this log 3/4 basically is tiny as long as
And that's
yeah.
It's an open question. Exactly what's going on.
Yeah. And okay, so and then later on, Bielowskaya and Van Handel in the follow-up work showed that this kind of result also extends to the non-Gaussian model. So here we have x as a sum of general independent matrices xi, where each xi has bounded norm, almost sure bounded norm, bounded by rho. And then essentially we can get an error bound of 2 sigma x plus the non-commutativity parameter, which is given in red, and also this purple thing over here, which is sort of some geometric mean between sigma and rho that sort of measures how close to Gaussian it is. So this purple thing here measures how close it is to Gaussian, and this red part measures how close how sort of well-behaved the Gaussian part that is. Yeah. So essentially, basically the idea is as long as nu is much less than sigma, and as long as this rho is much less than sigma, all of these errors is very small, and you get a very tight bound of 2 sigma x. Yeah. Okay, so yeah. Yeah.
So the big difference here is that we still have log d, but it's only additive instead of polynomial.
Right.
So that's why we're really happy.
Yeah.
Can u of x be bigger than sigma of x?
Yes.
I see.
Yeah.
So that's why this is not an improvement over the previous bound.
Right. And in fact, I'm actually going to get to it in this case. So if we go back to the previous example, if you look at the diagonal matrix, which is fully commutative, you can verify that nu and sigma are the same, and you have no improvements, as Eric just said. But if you consider the GOE setting, because all the entries are independent and you're scaling them to have sigma equal to 1, the new parameter is on the order of 1 over root d. This means that when you plug in that bound, you get something like 2 plus 1 on the order of 1, something that's on the order of 1 over d to the 1/4, which means you get a very sharp decaying error term. And yes, so
you get something better on the left-hand side. Before we had log of d, now we have log to the 3.
Yeah. Yeah, before it's root log d, now it's log to the 3. Yeah.
Oh, I see.
Yeah. Right. So basically, going back to what I said earlier, so if nu x is small, it means that the randomness of the matrix is sort of more well spread over its entries. Why? Because nu x, again, is the maximum eigenvalue of the covariance matrix of the random matrix as a vector, right? So it basically tells you that the randomness is well spread over this d squared dimensional vector space spanned by its entries, right? There's no one direction where you have a lot of randomness in that direction. Yeah, intuitively, you can think of it that way. Okay, so what does this have to do with free probability from the title? Well, essentially, the approach that they took in this work is something called the comparison approach, where they compare the spectral statistics of x with that of a certain infinite dimensional operator called x-free from free probability, instead of bounding the eigenvalues directly. So they compare these two things instead of bounding directly. And using basic properties from free probability, you can show that the norm of this operator is upper bounded by 2 sigma x. And again, I'll get into more details about what this operator actually is later, but yeah. Yeah, so I will talk more about what is free probability. It's for now just it's a branch of mathematics that is kind of abstract and scary. Okay, okay, so yeah, and they study operators in that field. Okay, so this operator, this linear operator, has operator norm almost 2 sigma x, and the comparison approach just tries to basically says that the norm of x, the expected norm of x, is basically close to the norm of this operator. And then from there, you can use some operator theoretic trick to show that then the norm of the operator is upper bound by 2 sigma x. And this is how you get those kind of bounds. Yes, and then if we apply some Gaussian Lipschitz concentration inequality, we can also prove tail bounds of the norm around the mean. Yeah. Okay, so this is the general approach of BBBH. So what do we do in this paper? We basically de-randomize these matrix concentration inequalities. In particular, given a certain random matrix model X, we deterministically find a matrix Y in the support of this random matrix. So we deterministically find an outcome that satisfies those concentration inequalities that we showed earlier. So why is an interesting question? Well, first of all, de-randomization is a pretty fundamental question in computer science, right? And moreover, these matrix concentration inequalities have many algorithmic applications. So by de-randomizing them, we get a powerful tool, algorithmic tool that you can use to attack many kinds of de-randomization questions in different areas. So in general, a very good tool. And also, maybe if you're more interested in the mathematical side of this, it sort of gives us a new perspective on these free probability results. In particular, I think a nice outcome of our proof is that we actually derive through new proofs of those bounds from BBVH and their follow-ups based on classical algorithms from theoretical computer science. So it somehow gives us an interpretation of these mathematical results that's more friendly to maybe computer science people. Yeah. Yes, and another interesting thing that we observed is that not only can you use these sort of properties of these free operators to bound the eigenvalues of random matrices, but you can also use them for efficient computation. Okay, so I'll elaborate on these things later in the talk, but this is sort of like generally why we're interested in this question. Yeah. So again, let's compare our results with some classical results. So maybe you guys are familiar with matrix turn-off bounds and these kind of things. And basically, back in 07, 08, people like Wigderson and Xiao and Aurora Cowley de-randomized these classical matrix concentration inequalities using techniques like pessimistic estimators or matrix multiplicative weights. And this led to deterministic algorithms for spectral specification and SDP rounding and expanded graph construction, all sorts of nice deterministic applications in computer science. So it is well known how to de-randomize those classical inequalities. But the new inequalities are sort of have been so far much more elusive because they're kind of complicated. But they also have some really nice new applications that could not be obtained before in areas ranging from matrix discrepancy to statistical estimation and to the construction of Ramanujan expander graphs, which I'll go in more details later. But basically, by de-randomizing their concentration inequalities, we can get deterministic algorithms for all of these applications. And moreover, in our paper, we actually give two algorithms. The first one, called the deterministic Brownian walk algorithm, is for de-randomizing those Gaussian inequalities from BBVH. And then the second one, called this deterministic iterated exchange algorithm, is for the non-Gaussian setting. Okay. So yeah, so overall, I think, yeah, so it's a very nice tool bag for us that we can now use.
Question.
Yes.
So here, how do I understand this slide? Is it like your results, do they help with the randomization of these constructions?
Yes. Yes. They give the randomizations of all the applications that were that arises from the random results. Yeah. All right. Okay, so this is anyone have any questions about the broad overview? Okay. So no questions. I'm going to get in. Now I'm going to explain, sort of give a quick crash course on free probabilities. Yeah, so for those who are not familiar. So free probability is essentially the abstract study of non-commutative random variables. So what I mean by non-commutative, like consider when you have a random matrix, right? You can either consider this as a matrix whose entries are commutative random variables, or you can consider the entire matrix as one big random variable that's non-commutative under multiplication. And so to sort of study these things, we define like an abstract non-commutative probability space as a pair A tau, where A is a unitary algebra over the field C, and its elements are referred to as the random variables. Right? And then this tau is basically just a linear functional on A that maps the identity to 1. And we sort of refer to this as the expectation functional. And this algebra A may have some additional structure. For example, it might have a norm on it and some star operation. And this tau might also have additional structure like the trace property, which says that tau of AB is equal to tau of BA. And in fact, throughout this talk, these additional structure will typically always be present in our examples. Okay, so this is a lot of abstract stuff, but let's see some concrete examples of this. So I mentioned earlier that you can study random matrices this way. Okay, so for example, we can take A to be the algebra of random matrices over the complex numbers. Maybe add the constraint that they have bounded moments or something like that, and then we define tau of x. So given a random matrix X, we define tau of x to be the expected trace of X. So here we see that indeed it satisfies this trace property. And moreover, and moreover, you see that you also have this star and norm operations as well on these kind of things. Okay, so this is a more concrete example. A slightly more abstract example. Consider when you have a Hilbert space, possibly infinite dimensional Hilbert space, and consider A as the set of bounded linear operators on this Hilbert space F. And suppose we have some unit vector in F. So and then given an operator, we define the tau, the expectation of this to be the inner product between omega and t omega. Right? So this is going to be a linear functional as well, and it's going to map the identity to 1. So this is still a non-commutative probability space. So essentially, so this sort of abstract view of non-commutative random variables gives us a unified way to study a lot of different things, from random matrices to infinite dimensional operators. And this is important because we want to eventually be able to compare these two. Right. So does anyone have any questions about the definitions? Yeah.
What exactly is a unitary algebra?
Oh, it contains the identity. A multiplicative. So an algebra is just a vector space where you can multiply the vectors, and the unitary means that the multiplication has an identity. Yeah.
So if I'm taking a classical probability space and I want to define it in this setting, what would A and tau be in this case?
Yeah. So for the random matrices, for example, so you mean a classical?
Just the standard ones we're used to.
Yeah. So for a classical commutative probability space, the A would just be the set of random variables over some probability space. Tau would just be expectation. Yeah. It would just be taking expectation. Yeah. And the unit is just 1. Yeah. In this case, the unit is the identity. Yeah. Okay. Does this make sense? Okay. All right. So now, okay. So what are some basic concepts in probability? Well, there's concepts like distributions and independence, and these are fundamental concepts in probability. And it turns out that we can also define non-commutative versions of these things. So for distributions, what is the definition of distributions? If you're given a set of random variables that are non-commutative, we define the distribution of these random variables to just be the value of tau, the expectation, evaluated on all polynomials, all non-commutative polynomials of these random variables. In other words, the distribution is just defined by the value of its moments. So why is this a natural definition? Well, remember that in classical probability, whenever you have the moments, the joint moments of a bunch of random variables, you can also obtain the joint distribution through some inverse Steele's transform. Right? But it turns out that for non-commutative random variable, there isn't a nice notion of a joint probability distribution as like a measure over Rn or something like that. But we can still define the moments. So that's essentially what you have to use to study these joint distributions. Yeah. And probably the most important concept in free probability is the notion of free independence, which is a notion of independence for non-commutative random variables. So here I have written out the definition of free independence, what it means for a set of random variables to be independent. You can take a moment to look at this if you like, but basically for the rest of the talk, you don't need to know you don't need to remember like this exact definition. What you really need to know is just that when you're given a set of freely independent random variables, or sometimes we just say free random variables for short, if we know the distribution of each AI, then we also know the joint distribution of the whole thing. And again, should be familiar from classical probability, because in classical probability, if you know the distribution of each random variable, you know the independence, you also know the joint distribution. Right? So this is also true for non-commutative things. So,
as obvious as just multiplying them or something. So
no, it's a little bit less obvious, actually. So you have to start from this definition and show that essentially you show that if you know what the value if you know what the moments of each individual random variable is, then through some basic computation and applying the previous definition, you can essentially compute the moment of any polynomial. I mean, the expectation of any polynomial of these random variables. Yeah.
But it's not as simple as, for example, if the polynomial is, let's say, like a1 squared a2, it's not like I would say tau of a1 squared times
So that would be classical probability. So yeah, it's not true that the expectation factor. Yeah, but it's still computable. Yeah. Yes. Yeah. So now a fundamental result in free probability when it was first sort of discovered is based on the limiting distributions of Gaussian matrices. So remember that in our example of like the non-commutative space of random matrices, that if we're given a random matrix X that is symmetric, and if you look at the expected trace of X to the power of P, you can write this as the expectation of lambda average to the P, where lambda average is a uniformly random sampled eigenvalue from X, right? So in a sense, you can think of the moments of the random matrix as the moments of a random variable that is commutative, that sort of gives you the spectral distribution of this random matrix. And remember that remember a definition of GOE random matrices, which is just symmetric Gaussian matrix with independent entries. And it turns out that as the dimension of these GOE matrices go to infinity, the distribution that there's a limiting distribution for their eigenvalues. So in particular, we know that odd moments vanish by basic computation, and the even moments converge to the Catalan numbers, as it turns out. So if you take the limit as n goes to infinity, the expected trace of the moments, the expected trace of the matrix to the 2p converges to the pth Catalan number. This is a classical result from random matrix theory. And what this tells you is that the distribution of an average eigenvalue of X follows the distribution of a random variable whose moments are given to you by this Catalan number. And in particular, the probability density function of this random variable is exactly the semicircular function, which is just if you draw a semicircle, that's exactly the probability density function. Yeah. So does this make sense? This is like a classical result from random matrix theory. Yeah. So if I plot the eigenvalues of a random GOE matrix, they will eventually start looking like this. Okay. Okay, but so that's the distribution of one GOE matrix. What about the joint distribution of a bunch of GOE matrices? So fundamental result proven by Wojciechowski when he discovered free probability is that if you have a bunch of independent GOE matrices, then in the limit as their dimension go to infinity, that these matrices become asymptotically free or freely independent from each other. So in other words, essentially all of those polynomials from the definition of free independence that are supposed to go to zero will go to zero on it, yeah, in the limit. Oh, what happened? Okay, so because of this, we can represent the sort of the limiting objects. We can sort of define these abstract random variables to represent the limiting objects as you take the dimension of this matrices to go into infinity. Yes? Yeah.
Here, previously the independent definition was that if any of those or all of them are equal to zero, then the joint thing should be zero.
Yeah, basically for a certain set of polynomials, we want the expectation, or I guess the expected trace of those polynomials to be equal to zero. And as long as all of those go to zero in the limit, then you have asymptotic freeness. Yeah. So because of this, we can sort of define these abstract random variables called the free semicircular family of random variables, S1 to Sn, which sort of captures the limiting Gaussian matrices.
All values are independent of the n, right?
Sorry? You mean for
Yeah,
Which n? You mean the little n or big n? Sorry.
the big N, this side of the matrix.
Yeah, so for the matrices, the values are dependent on n, but as n goes to infinity, then these S1 to Sn
Yeah,
little
but
independent of
taking
n.
traces and the trace could go to non-zero while each value goes to zero. But it's a small point, but that's what's going on in my head.
Oh yeah, so the trace is a normalized trace. So you always normalize by the dimension when you take the
Okay,
trace.
fine.
Yes, yeah.
Yeah.
Okay, so when we define these random variables, we say that each Si has the moments where the odd moments vanish and the even moments are given by the Caroline number. And the joint distribution of these random variables is characterized through free independence. Right? So once I have this abstract definition, the asymptotic freeness property basically tells you that for any non-commutative polynomial P, the expected trace of these Gaussian matrices, the expected trace of P of these matrices will converge to the tau, the expectation of this polynomial P of S1 up to Sn. Right? So in other words, the expectation converges for all polynomials. Right? So again, if you remember definition of weak convergence from classical probability, you can characterize it as saying like all the moments converge to the moments of the limiting thing. This is basically also saying that all the moments converge to the moments of the limiting thing.
So this is like, are you saying existence, there exists S1 to Sn
Yes.
such that
Yes.
this is true?
Yes. Yeah. Yeah. I mean, technically, as soon as you define the moments and you say that they're free, immediately they exist because you can just compute all of their moments. Right? Once you define all their moments, then they exist. Yeah. But an interesting point is that not only do they exist, but they can actually be concretely. Oh, sorry. Yeah, I forgot to mention that you can also extend this to like continuous functions if you take limits and stuff like that. Yeah. But yeah. So as I was saying earlier, the S1 up to Sn can also be realized concretely as self-adjoint operators over a certain infinite dimensional Hilbert space. So what I mean by this is that there is some set of operators living in this abstract over this abstract Hilbert space, such that if I look at the moments of these operators, they match the moments of this semicircular things that I just defined.
So it's not just like,
Yeah.
so you have explicit way in which you can.
Yes. Yeah, I have some explicit way in which I can build these things as infinite dimensional operators. And okay. Oh, sorry. No. Okay. Yeah. So basically, because I have these explicit constructions, now I can define my X-free operator that I was alluding to earlier. So suppose you have a Gaussian random matrix X equals A0 plus summation IGIAI. We first define a bigger lifted Gaussian matrix Xn, which you can write as A0 tensor identity n plus summation IAI tensor AI GIN. Basically, you're replacing each Gaussian scalar random variable by n by n GOE matrix. And then when you take the limit as n goes to infinity, what you'll get is then you'll replace each Gaussian GOE matrix by a semicircular random variable. Yes. IN is the identity matrix, yes. And this one is just the identity element in the infinite dimensional space. And then, so here's a concrete illustration of this. So suppose my matrix looks like this, right? So Gaussian matrix means each entry is a linear combination of independent Gaussian variables. So Xn is basically like saying we have a matrix with matrix entries where each entry is the same linear combination of these GOE matrices. And then when we take the limit, it is a matrix of semicircular random variables where each entry is the same linear combination of those free semicircular random variables. So that's what X-free is concretely. It's a matrix of semicircular random variables. Okay. So now okay. So what are some nice properties of this X-free? First of all, as I alluded to earlier, the norm of this operator can be bounded by the norm of A0 plus 2 sigma x. So in particular, we can get a bound on the norm that's independent of the dimension d. So there's no log d factor when it comes to this norm. And moreover, the moments of this infinite dimensional operator can be computed exactly in polynomial time. And again, here's a formula for it. You don't need to remember this formula, but you can the idea is that you can write the partial trace of some power of this matrix as some function of the partial trace of smaller powers of this operator, sorry. And using the dynamic programming by storing all the previous things, you can basically compute this in polynomial time. So the idea is, yes?
Sorry, what is X3 an operator on? Is it an operator on?
Yeah, so it is actually an operator. It would be an operator on like Cn tensored with the Hilbert space that these S's are operators on. Yeah, I mean it's just a matrix. Just think of it as a matrix whose entries are operators. It's a tensor between like a finite dimensional space and an infinite dimensional space. Yeah, just operator norm. Actually, okay, so because these things are self-adjoint, you can also define it as a maximal eigenvalue. Yeah, so you can look at I mean, you can define the eigenvalue of the operators in the standard way, and then this is just the biggest eigenvalue, basically. Yeah. Okay, so so essentially the weak convergence result tells you that whenever you have a continuous function, then the expected trace of this function of the matrix will converge to the trace. Well, in this case, yeah, it will be the trace in the tensor space, but the trace of this of the same function applied to this X3. Yeah. And yeah.
Sorry, I'm confused. Where are these A's living? Right, in the earlier examples when we were doing GOE, A was something like a coordinate vector tensor itself, so it was living in dimension n.
Uh-huh.
But now A somehow is not living in dimension n. So
you mean this A, the capital A? Oh yeah, these are just matrices, right? These are D by D matrices.
so there's another D separate.
Yeah. So X is a D by D matrix, right? So here you see X is living in D by D, C D by D. Xn is living in C dn by dn, right? Because you're lifting the matrix to a bigger matrix where each coordinate becomes a matrix now. And then in the infinite dimensional case, I'm looking at C D by D tensor A, where A is the algebra of these semicircular things, but the C D by D is still just
replacing multiplication by the scalar GI multiplicate tensor product.
Yeah. Yeah. Okay. Right. Okay. So now I've spent all this time trying to explain the basics of free probability. I can sort of explain how those results were proved in these recent papers. So basically, once you have all of this, we basically show that we basically have to just pick a suitable function, and we want to show that the expected trace of this function on x is close to the expected trace of this function on xn. Right? So here x and xn are both Gaussian matrices, right? X is a Gaussian matrix, xn is a lifted Gaussian matrix. But we basically want to show that the spectral statistics of these two matrices are close to each other. And then by taking limits in n, you immediately have, and if you show that these two things are close by taking limits in n, you can immediately compare the trace of x with the infinite dimensional thing. Yeah. So as an example, we can look at their moment concentration inequalities. Yes.
Somehow to use the bounds on x-free operator to bound x.
Yes. The final goal is to use the bound on the x-free operator on x. But to do that, you define this intermediate xn, which is this big lifted matrix. And then you show that the spectrum of this lifted matrix is close to the original matrix. And then by taking the dimension to infinity on this lifted matrix, you get x-free. So then that means x is close to x-free. Yeah. So to give a concrete example of this, let's say our interpolation function is just a polynomial, right? X to the 2p, right? So basically what you first show is that the expected trace of x to the 2p is close to the expected trace of xn to the 2p, right? And the error is bounded by our new parameter, right? This geometric mean between sigma and nu. And then you take the limit for this xn to get x-free, which tells you that the expected trace of x to the 2p is close to x-free to the 2p, plus our error. And then, and this holds by weak convergence. And then by using the properties of x3, then you can then bound the operator. You can then, let's say, bound the p norm of this operator by the infinity norm, and then bound that by 2 sigma x. And then this is how you can bound the moments, the expected moments of the original matrix by 2 sigma x. So yeah, the step 1 is based on weak convergence. Step 2 is based on some abstract operator theoretic properties. Yeah, and the combination of these two steps gives you our sharp matrix concentration inequalities. Okay, so what is our first result? We show that there is a deterministic algorithm to find a vector x that satisfies this bound. So first, we want the norm of the vector to be at least n, so that it's the square norm to be at least n, so that it is well defined. So this is non-trivial. And then we want the trace of a0 plus ax to the 2p. We want the Shatton p norm of this matrix a0 plus summation I ai xi, which we denote as ax, to be upper bounded by the trace of the infinite dimensional operator plus our error term. So yeah, we just found a deterministic sample vector satisfying this concentration inequality above. And okay, so actually, does anyone have any questions about this? So this is essentially the flavor of all of our results. Okay, so but actually, in a lot of applications, we actually want to round this kind of fractional x to some kind of integer x, right? Because in computer science, we actually care about integral things. And there's a result by Rothfuss which says that any convex body that has large enough Gaussian volume has to contain a point with many plus minus 1 coordinates. And with this kind of result, what we can, and essentially, moreover, his argument comes with a randomized algorithm to find such a point. So our second result is to actually de-randomize the application of, de-randomize a version of Rothfuss's projection result combined with this free concentration inequality. So in particular, for any large enough subspace H of Rn, I can find a vector x in the subspace where each coordinate is bounded by plus minus 1, and half the coordinates are in plus minus 1, or equal to plus minus 1. And again, I want the moments of this matrix of the matrix when signed by these vectors to be upper bounded by this kind of sharp concentration inequality. So why do we care about this kind of geometric, this kind of integral coordinate result? Well, this is closely related to our first application, which is in matrix discrepancy theory. And so basically, a classical result is the matrix Spencer conjecture, a classical conjecture in discrepancy theory called the matrix Spencer conjecture. Basically says that if you're given a set of symmetric if we're given a set of symmetric n by n matrices, where the norm of each guy is bounded by 1, does there exist a plus minus 1 signing of these matrices so that the norm of the signing is upper bounded by root n? And so you have n matrices of n by n. And
It's the sign itself.
yes, yeah, the sign set. And okay, so notice here that if we pick a random signing, the sigma squared of the signing is at most n. And if we want to apply these concentration inequalities, we see that the nu squared parameter, as long as the nu squared parameter is bounded by n over log cubed n, then such a signing can be found. It was shown by Bensel, Jiang, and Mecca that actually you can find a good signing whenever the rank of each AI is bounded, which was actually a really big breakthrough in the matrix Spencer problem, because previously people only know how to do this when the rank is at most root n. But now they can do this when the rank of the AIs are at most n over log cubed n. So yeah, this is a big breakthrough. And essentially all they did was to do a simple application of this BBVH concentration inequality. And as an application, we basically give a deterministic algorithm to find such a signing. And the general idea is that essentially we apply this partial coloring result where we find a good subspace to project the input matrices in, so that when we project them, the low rank condition actually translates to this new square thing being small. And this allows us to sort of sign at least half the coordinates of x. And then you just repeatedly apply this thing over and over again, where each time your error sort of geometrically decreases. And this is how you do your signing. Anyway, the details of this is not super important. The main thing is that we can find a de-randomization of this result. Okay. And then our next result is that the next result of BBVH is that they actually prove a concentration of the entire spectrum of X, which is something that's much stronger than just looking at the norm over the moments. And here we define, so given two subsets of R, we define the Hausdorff distance between these two sets to be this quantity over here, which essentially this thing is small. If this thing is small, it means that any point in B is close to some point in A, and every point in A is close to some point in B. So this is some way to measure the distance of two sets of R. And what they showed in BBVH is that actually with high probability, the entire spectrum of the random matrix X is close to the entire spectrum of the random matrix X free. An infinite operator X free. So visually, it might look like this, where if the yellow part is the spectrum of X free, the sort of histogram of the eigenvalue of X has to concentrate within this region, basically. And this is essentially done. So this is essentially proven by controlling these things called resolvents. But again, this kind of detail is not super important for now. But basically, the idea is that they apply the same framework where by finding an appropriate, by controlling an appropriate function of the matrix X and comparing it with that of X free, you can sort of translate this to a bound of the entire spectrum. And our next result is that, again, we deterministically find a matrix. We deterministically find a vector such that we deterministically find a matrix within the support of X such that the distance between the spectrum of this matrix that we constructed and the free operator is bounded. Yeah. And then this sort of, okay, so we're running a little bit close on time, so I won't really get into too much detail on the application of this result. But basically, the idea is that using this result, you can actually control the behavior of not just the eigenvalues of random matrices, but also the eigenvectors of random matrices. Yeah, but I will sort of not go too much into this for now. So the final result that we de-randomize is the universality result, which basically tells you that the behavior of non-Gaussian random matrices are also closely approximated by those of Gaussian matrices. So in our general model, we have a random matrix Z, which we can write as A0 plus summation I Zi, where the expectation of each Zi is 0, and the norm of each Zi is bounded by some rho, almost surely. And the idea of universality is that if we define a Gaussian matrix that has the same mean and covariance as this matrix, then sort of the eigenvalues of these two matrices are close to each other as long as this rho parameter is small. So in particular, and this is actually in fact exactly what they showed in this follow-up work, which is that the spectrum of the Z, this non-Gaussian Z, is very close to the spectrum of this Gaussian matrix X, as long as this rho parameter is much smaller than sigma. And moreover, if you combine this result with the previous concentration inequality on the Gaussian matrix, you can show that the spectrum of Z is close to the spectrum of this free operator. So how do we de-randomize this kind of result for general matrices? Well, basically, the idea is that instead of trying to compare the eigenvalues of a random matrix with a Gaussian thing and then comparing the Gaussian thing with the free operator, we directly compare the eigenvalues of the matrix with the free operator. So we basically skip the step of going to a Gaussian matrix. Yeah. And so in our result, we also make the assumption that each of the ZIs have polynomial support sets. So in some sense, each of the ZIs is sort of a simple matrix to work with, but the sum of these independent ZIs is different. That can still have very large support sets. And what we show is that there's a polynomial time algorithm to find a matrix Z prime in the support of this, so that the norm of this matrix is upper bounded by that of X free. And the key application of this result is in the construction of near-Ramanujan graphs. So when you're given a K-regular graph with adjacency matrix, with a D by D adjacency matrix, which means the graphs D over D vertices, we know that the top eigenvector of the graph is the all ones vector, and the top eigenvalue is k. And the second eigenvalue of this graph essentially measures the expansion of this graph, which means that the second eigenvalue is small, if and only if the neighborhoods in this graph are fast growing, and if and only if the random walks on this graph is fast mixing, and so on, right? So it has a lot of nice combinatorial properties. And this kind of object is very useful for the study of pseudo-randomness, coding theory, and lots of things. So it is a very important object in computer science. The classical Alam-Balpana result says that sort of asymptotically, the best possible expansion you can have on a graph is 2k minus 1. And if the expansion is indeed upper bounded by this, then it is called a Ramanujan graph. So this is sort of asymptotically the best possible expander that you can have. And a fundamental question in math is whether or not there exists constructions of Ramanujan graph, first of all, for all possible degrees and size, and whether or not these things can be made deterministic, right? So the deterministic part is important because sort of these Ramanujan graphs are sort of seen as pseudo-random objects. So then an interesting question is, can we construct them without randomness, right? So you may have heard of, okay, so basically it is well known that actually the graphs are pseudo-random in the sense that random graphs are optimal expanders with high probability. And in particular, if I define a random regular graph to be the union of a bunch of perfect matchings, then this thing is going to be close to Ramanujan. So in particular, suppose I define a random graph as follows, where the adjacency matrix A is written as a sum of pi I pi transpose, where each pi I is a random permutation matrix. So this you can think of as a deregular graph that you get from the union of a bunch of perfect matches. And a classical result of Friedman is that this thing is in fact near Ramanujan. For any fixed degree k, if you take the size of the graph, if you take the number of vertices going to infinity, this thing is near Ramanujan. And Bordenov later on gave a sort of a simpler proof than Friedman, and his proof was de-randomized by Mohanty, O'Donnell, and Paredes in time that is sort of polynomial if degree is constant, but not polynomial if degree is not constant. So then a natural question that we might ask is what happens for non-constant degree, right? So we know that in constant degree regime, this de-randomization works, but what happens for non-constant degrees? And one of the results of these free concentration inequalities is that these things can be de-randomized essentially for free by directly plugging in their bounds whenever the degree is at least polylogarithmic in the size of the graph. Right? So this sort of covers the complementary regime of Friedman's result, which sort of only works when the degree is constant. And our de-randomization basically gives a deterministic constructions of these Ramanujan graphs in this high degree regime. Yeah, which is again, it is not known how to construct these dense near Ramanujan graphs before. And okay, yeah, and then basically the key observation is that if you replace these independent random matchings with sort of pairwise uniform random matchings, if you replace these uniform random matchings with the simpler close to uniform but smaller support size random matchings, it still works. Yeah, it's always polynomial time. Yeah, it's polynomial regardless of the degree of the graph. Yeah. Okay, so yeah, I won't talk about this part because we're kind of running low on time. Okay, the clicker is not working. But basically, yeah, I'm trying to click through these. Okay, so I won't get into this, but basically there are other random graph models of constructing Ramanujan graphs based on lifts where our result also work. Yeah, but yeah, I won't get through. I won't really talk about this too much. So I just want to talk a little bit. Okay, this is try to click past this. Okay. Oh, okay. So I want to talk a little bit about our proof techniques because yeah, we're running pretty short on time now. But so I'll just give a really basic overview of how we prove these things. So okay, so basically the way that all right, this is I don't know what's happening right now. Yeah. Okay, yeah. Use this. Okay, sorry. So the basic idea of BBVH of how they compare the spectrum of X with Xn is that they basically define two sort of lifted matrix. One matrix is many diagonal copies of X, and the other one is sort of like a GOE matrix, but each entry is a copy. Well, I mean, sorry, the other one is just Xn, right? So one of them is Xn, which is summation, which is the AIs tensored with the GIs, and the other one is just many diagonal copies of X, which has the same eigenvalues of X, which has the same spectral distribution as X. And you just do a basic interpolation between these things, these two quantities by, you have some potential function, let's say the moments, and you basically just write the difference between these two matrices as integral of the derivative of this potential function. And right, but this kind of approach is difficult to de-randomize for a variety of reasons. But the main reason is that we don't know how to compute these potential functions in polynomial time. So the main idea that we use is that we define an interpolation scheme between X and X free directly without going through this Xn matrix. So what do I mean? Well, consider a random Brownian motion, xt, where xt is a Gaussian with where xt is a Gaussian with variance t, right? So, and then we're also going to define, so we're going to define axt as being just summation I, ai xt of I, and then this, we're going to define this as as being the summation ai tensored with the si's, the infinite dimensional si's. And we're going to define this mixed operator that sort of contains a finite dimensional part and an infinite dimensional part. So the finite dimensional part is this a0 plus axt, tensor 1. And then the infinite dimensional part is as. And I want to just do an interpolation between x and x free in this way, where you see that when t is equal to 0, this is equal to x free, because all the mass is on the free part. And when t is equal to 1, this is equal to x, because all the mass is on the finite dimensional part. And we basically want to say, okay, so let's define some potential function, where, for example, the potential function of x t, there shouldn't be an over here, but the potential function of xt is just its trace moments or the trace moments of its resolvents or something like that. And we basically just want to sort of bound the rate of change of this potential function as I go from x0 to x1. So this is the general approach. And the key to why this resolves the main issue of trying to de-randomize BBVH is that using basic properties from free probability, you can actually compute all of these potentials in polynomial time. Right? So these things are not easy to compute if these are random matrices, but they're easy to compute when these are actually infinite dimensional operators. This is the key behind our approach. And okay, so from here, we can basically do the interpolation by first discretizing the interval t into some small step sizes. And at each small step size, we say that conditioned on a previous xt, if I update xt a little bit, the change is small. So the expected change is small. And then I want to claim that actually we can deterministically find an update where the change in potential is upper bounded by the expectation. Right, so this is the two steps. Now from here, okay, and basically the key to how to actually bound this potential update is to make the crucial observation that when you're given a Gaussian vector x, right, you can write, when you have this Brownian motion x, and you want to look at xt plus eta, you can write this as xt plus root eta times y, where y is an independent Gaussian. Right? Because the sum of independent Gaussians is still independent. It turns out that for semicircular operators, this thing still holds. So if you have this root y minus t times si, you can write it as root y minus t minus eta times si plus root eta times si prime, where si prime is freely independent from si. To see why this is the case, just remember the fact that si is essentially an infinite dimensional representation of a big GOE matrix, right? So if you add two independent GOE matrices together, the result is still GOE because all the entries are linear, right? So if you add these things together, so this means that if you add two freely independent semicircular things together, there is still going to be semicircular, right? And by just using this, we can essentially write x t minus eta and xt as the same matrix that only depends on t plus either a random Gaussian update or a random free update. And to interpolate between these quantities, we just have to do a Taylor expansion of this quantity and take the difference in the Taylor expansion between these two terms. So, right, so we can write our potential applied to xt eta plus some update as the original term plus the first order term plus the second order term plus some small things. And then the key thing to realize here is that if I take h to be ay, it is independent from this xt eta over here. And if I take h to be as prime, it is freely independent from this xt eta over here. So this essentially tells you that the first order term always vanishes, and the difference in the potential is only given to you by the difference of the second order terms. And once you have this part, then you can use some techniques from BBVH to balance second order terms, and this will give you your interpolation. And as for how to de-randomize this thing, essentially the key to notice here is that this change in potential, because it only depends on the second order term, I don't actually need y to be a Gaussian vector. I just need it to be something, a random vector whose second order statistics match those of an independent Gaussian. So I can pick it to be random plus minus one vector with pairwise independent entries. And this is a much easier thing to work with than Gaussians, because then I can just iterate through the entire samples, the entire support of this y, and I can get the bound. And I can deterministically find a vector satisfying this bound. Right? Okay, so because we're pretty much out of time, I think we can conclude the talk around here. I won't go into the proof details of the rest of our results, but this is really the key. This part is really the key sort of behind all of our arguments, is that you can do this interpolation between you can do this interpolation between a Gaussian matrix and a free operator using a Brownian motion, and you can de-randomize each step of the update to this Brownian motion using a pairwise independent vector, which then you can sort of iterate through the entire sample space of this to de-randomize. Yeah. Okay, so yeah, that concludes the talk. Yeah, if anyone has any questions, feel free to ask me afterwards, because I'm pretty much out of time now. Yeah, so thank you. All right.